Hello, mathematicians, and this is Mr. Garcia, and we're back today with a new lesson. Yay! So today we're going to be talking about arc length and sector area. This is lesson 8.7. Let's start with our objective so we know what we're learning about. I can find the length of an arc and the area of a sector using proportional relationships. So let's start by defining what each of these words mean, arc length and sector area. We're going to start here with arc length. So when I want to find the arc length, what that means is I'm looking for the actual length of an arc. Now, if we remember on what we've been talking about so far, we know that the arc is a piece of the circumference of a circle. So like here, arc BC is that much of the circle. Up to this point, we've been measuring our arcs in degrees, just like we measured the angles. And we remember that the central angle and the arc have the exact same measure. So if the measure of our central angle here is theta, then the measure of the arc is also theta. And remember that theta is just like x, it just means an angle measure that we don't know yet. So today we're going to talk about arc length though, and this is the measurement, the actual length of the arc. So if I took like a ruler, like a circular ruler, and measured how far the point C is from point D, that is the arc length. You think about it like a circular track. If you walk along that circular track, how far have you walked around the track? That's your arc length. So how do we find it? To find the arc length, what we need to do is first start off by figuring out how much of the arc do we have compared to the total circle. Because there's two things that I know for sure. I know that the total angle measurement around the circle is always 360 degrees. I know that. I also know that the measure around an arc is the same as the measure of the central angle here. And that the measure of the arc is just a piece of the central angle. So I have a piece of circle over the total circle, right? This would be the arc, and this would be the 360 degrees. But there's another way to have a piece of a circle and a total circle, because that other way is to have the arc length, which is what we're talking about right now. And so what can I do to find the total length around the circle? The total length around the circle is the circumference, right? So if we know the circumference, we can use that to compare with the arc length, and what do you know? We have a proportion. So let me erase some of this. And I could have the circumference be my total. So I want to set up a proportion then so that I can cross multiply it, and that will lead me to whatever the arc length is. So let's set it up to see what that would look like. First, I know that I need the measure of the arc. Measure of arc. And what goes under that is going to be the total measure of a circle. Measure meaning the angular measure, meaning 360 degrees. And I want to compare that now to the lengths, which means the arc length and the circumference. Now my arc length, I have it in purple, so I'm going to write it in purple here. So I have the arc length and the circumference. You see I have the circle in red, so I'm going to write that in red. And I misspelled circumference. There we go. So with this relationship between the angular measures over here and with the lengths over here, I have now set up a proportion that I can cross multiply and use to solve for the arc length. And in fact, I could use this to solve for any of the pieces as long as I have the other ones. So if I want to find the measure of the arc instead, then all I need to have is the arc length and the circumference. If I wanted to find the arc length, then what I need is the measure of the arc and the circumference and so on. Now, since our goal here, though, is arc length, we can also rewrite this formula a little bit to help us solve for the arc length instead. Now, what I'm going to do next, though, is replace all these words here with the symbols that we're using in our circle. So the measure of the arc, we're using theta for that. So I'm going to have theta over 360 degrees equals, and on the other side I have the arc length, which I'm using a cursive L for, and I have that over the circumference. But we know the circumference is 2 times pi times radius. So to get a formula just for finding the arc length, I'm going to cross multiply those, and so I get 360 times the arc length L equals theta times, now use a dot for that, times 2 pi r. Now since I'm solving for L here, I want the arc length. That means that on both sides, since I'm multiplying by 360 over here, then I'm going to divide both sides by 360 to cancel that out from the left hand side. And so what I end up with is L equals theta times 2 pi r over 360. Now that's a generalized formula that I can use to find the arc length. Of course, we can always remember to set up the proportions as well. If that helps you remember, the proportion, we have the angular measure of the arc over 360 equals the arc length divided by the total circumference. Or in symbolic form, we have it over here. All right. So that is arc length. Now let's talk about sector area. And you're going to find that sector area is almost the exact same thing that we just talked about with arc length. Except now, since we're talking about area, instead of circumference, we'll have area. So we're going to start off the same way. We need to set up a proportion between the angular measure of the arc and the total measure of the circle. So we know that our angular measure here is theta. So I'm just going to go ahead and start with the symbols this time. So I have theta over 360 degrees. And that equals, now this time, I want the sector area. So instead of having a cursive L, let's use a lowercase a for area, for sector area in this case. And we know that we need the total area. But how do we find the total area of a circle? Well, hopefully, a long, long time ago, when we talked about area, you'll recall the area formula of a circle. The area formula is pi times r squared. So pi times the radius squared. So knowing the area formula of a circle, now we have our proportions set up. And again, we're going to cross multiply this. So here's the first cross, here's the second. On the left-hand side, we'll have 360 times our lowercase a for the area equals, on the right-hand side, we'll have theta times pi times radius squared. And just like in the arc length, to get this variable by itself, I'm going to need to divide by 360 because that's going to cancel that out. But I do that on both sides. And so now I end up with a equals theta times pi times radius squared over 360. And so we can use that formula to find the area of a sector of the circle. And again, our proportional relationships, I have that down here. The angular measure of the arc over 360, same left-hand side that we actually have for the arc length as well. So we have the angular measure of the arc divided by 360 equals the sector area divided by the total area. And like I said before, we can also use this to find anything else that we're missing. So for example, right now, usually we'll be missing the sector area. So we need the angular measure of the arc and we need the total area. But if we were missing the angular measure instead, if we were missing the measure of the arc, then we would need to know the sector area and the total area. So we can use this relationship to not just solve for the sector area, but to solve for any of these pieces that we might be missing. And again, here is our symbolic representation of this proportional relationship. All right. Well, if you have questions, make sure you go back and you look at the previous two slides to help you understand it. We're going to go over some examples now, 4 of them exactly, so that we can put these formulas and these relationships to practice. But let's start with example 1 here. We need to find the length of arc AC. Now, it'll be very clear if they're asking for the measure of AC, which is what we've been doing in the previous assignments, or if they're asking for the length of an arc. So if they're asking for the length, that means we're going to have to use this formula or use this relationship. I want to use the proportional relationship in this example just to show you how I set it up. And later on, I'll use the formula so you can take a look at that one too. So first, I know that I'm going to need my arc measure and I'm going to need the length of the circumference. So let me start by putting up our proportion. So I know that I have theta over 360 degrees equal to the arc length divided by the circumference, which is 2 times pi times r. That's another thing that I want to point out too. If they're asking you for the length, make sure that over here you have 2 pi r, which is the circumference. In contrast, if they're asking you for the shaded sector or the area of a sector, then you're going to need to put pi r squared instead. Keep an eye out for that. So before I cross multiply, I'm going to go ahead and plug in my numbers, because that's going to make everything later on a little bit easier. So I'm going to start with my arc measure. And it tells me here that the measure of the arc is 40 degrees. So I'm going to put 40 over 360 equals L. I don't know L. That's what I'm looking for. But then here, 2 pi r, I know that r is 3. The radius is 3 here. So I'm going to put 3 in there for r. Now, when I'm solving these kinds of problems, sometimes I'm going to have to reduce the fraction at the very end. In this case, we're going to talk about also finding these answers and leaving them in exact form. And what that means is that I want to leave my answer in terms of pi. So I want to have a number here and then pi hanging on to it. We kind of talked about this a long time ago, but we never really touched it. So I'm going to show you how you can also write these answers in exact form. Now you can always use the decimal approximation too and just round it, but I want to show you exact form because it's going to help you out in the future too, in future classes. So if I want to leave my answer in exact form, I need to start off right here, right now, reducing whatever fractions that I can. Whatever fractions that I can reduce right now is going to help me out later on. So I'm not going to have to reduce really big numbers. Right now, I see that if I cancel that 0 out, in other words, I'm dividing the top and the bottom by 10, then that leaves me with 4 over 36. But 4 over 36 can be reduced further because I can divide the top and the bottom by 4. 4 divided by 4 gives me 1. 36 divided by 4 gives me 9. So the fraction I can use here instead of 40 over 360 is 1 over 9. So I'm going to clear this out and I'm going to write my new fraction in place. 1 over 9 equals, over here obviously I can't do anything with the L, that stays as L, but on the bottom I have 2 times pi times 3. When I'm leaving my answers in exact form, I'm going to ignore everything with the pi. I'm going to pretend that it's not even there. Now if I ignore that pi, I still have to multiply 2 times 3. So let's do that. 2 times 3, I know that's going to be 6. Now here's the key though. When I want to leave my answers in exact form, that pi that you ignored, we're going to bring it back. When I'm working with pi, ignore the pi. Do everything else that's around the pi. In fact, you can treat pi like if it was an x or a y or any other variable. Just leave it alone and do everything else around the pi. So in this case, 2 times 3 is 6, and I'm just going to put that pi there next to it. So now I need to cross multiply here. So I'm going to cross multiply, and I have 9 times L, that gives me 9L equals 6 pi over, no, times 1. But 6 pi times 1 is still 6 pi, so I'm just going to write 6 pi. Finally, all I have to do now is divide both sides by 9 so that I can get that L by itself, and I end up with 6 over 9 pi. I can write the pi on the side like this, or I can write it together up on the top like this. But 6 over 9, now here's another thing though, because if I ignore that pi, 6 over 9 is a fraction that I can reduce. I know that if I divide the top by 3 and I divide the bottom by 3, then that works out for me. 6 divided by 3 is 2, and I bring the pi back. And on the bottom, 9 divided by 3 is 3. Now there's nothing else that I can reduce, so my answer in exact form is 2 pi divided by 3. Now, like I said, we can do this in exact form. You can still leave it in decimal though. If you choose to leave it in decimal, then you don't have to worry about simplifying this because you're going to be putting it in the calculator anyway. If I find the decimal approximation, in this case, it's going to be 2.09. And again, I can find this by plugging this part, 2 pi over 3, into the calculator. If I do that, I'll get my decimal approximation. And that's it. So here are the answer. Could be 2 pi over 3 in exact form. And I'll put exact form here. Also known as in terms of pi, or I can leave it as a decimal approximation. Either answer will work, although I do want you guys to practice the exact form, because in the future in Algebra 2 and Pre-Cal, you'll see that exact form. I want you guys to know what it is so you'll be prepared. All right, so let's take a look at the next example here, which is the same circle, same everything, same arc measure, same radius, but this time they're asking us to find the area of the shaded sector. So you see how the question now is asking for the area. So that tells me that I'm not going to be using the 2 pi r anymore. This time I'm going to be using the pi r squared. So I need to use this proportion, which is almost the exact same thing. The only thing that really changes is that pi r squared. So let's start off again. I'm going to write down our proportion. Those are my dogs in the background if you heard them. I should make a video about them one time. And then over here on the right hand side, now we have the sector area, which we're going to label with an A. And on the bottom, we're going to have pi and then radius squared. So we already know that our arc measure in this case is 40 degrees. So we're going to have 40 over 360 equals A over pi radius squared. We know the radius is 3, so we have 3 squared. Now, just like before, if I can reduce everything that I can right now, it's going to save me a lot of trouble later. So 40 over 360, we already reduced that over here. Now I already know that's going to be 1 over 9. And in case you didn't notice, it's over here. So I already know that 40 over 360 reduces to 1 over 9. So I'm just going to copy that down. Let me do this step in a different color. Change your color, bro. There we go. So 1 over 9 equals A over pi 3 squared. Now again, when I'm working with exact form, I know I want my answer in exact form. So I'm going to ignore this pi and do everything else. So this 3 squared, which is 3 times 3, becomes 9. And then I bring the pi back in. Boom. So now I'm going to cross multiply. I have 1 times 9 pi and A times 9. So on the left-hand side, I'll have 9A equals 9 pi times 1 is still just 9 pi. So now on the left-hand side, I'm going to divide by 9 to cancel this out, but that means I divide by 9 here as well. So for my answer, A equals 9 divided by 9 is 1, and I can ignore the 1. So really this is just pi. And there's nothing else to simplify here, so that's my answer. A is equal to pi. And of course, we all know the decimal approximation for pi is 3.14. So either of those answers will work. But remember, I want you guys to practice the exact form, although decimal approximation will be accepted. All right. So once we know the proportional relationship, we know what to plug in, and we know how to cross multiply, then this stuff is pretty straightforward, I hope. But remember, if you have questions, let us know. We'll be more than happy to help you guys out. On the next example, now we have the radius 4 inches and the measure of arc KJ is 160 degrees, and we want the length of arc KJM. So I'm not looking for this arc, even though they tell me that measurement. I'm looking for this arc here, for KMJ. So we're going to have to work a little bit more out here. First, let's start by writing down what we do know. So the measure of arc KJ is 160 degrees. So I'm going to put 160 degrees here. We also know that the radius is 4 inches. So I'm going to put a radius of 4. This time, what we're going to use is the formula. So remember that formula I showed you? Instead of the proportional relationship, it's important to know how to use the formula as well. So we're going to use our formula this time. So I'm going to start with L equals theta times, since this is length, we're going to have the circumference here. So I need 2 pi r divided by 360 degrees. So we know that we're finding the arc length, but before we can do that, we're going to need the arc measure. Now we don't have the arc measure for the arc that we want. We have it for the opposite arc. But remember our measure relationships. If I know that this angle is 160 degrees, I also know that the entire circle is 360 degrees, which means that I can subtract these two to find the measurement that I need. So if I subtract here, I end up with 200. So my arc measurement that I really need over here is 200 degrees. And then I have times 2 times pi times the radius, which is 4. And then all that divided by 360 degrees. Now at this point, if you just want the decimal approximation, then you can just go ahead and plug this part straight into the calculator, and that'll give you approximately 13.96. And since our unit is inches and we're using area, then we have inches squared. But like I said, I want to practice getting the exact form here. So to get the exact form, the next thing that we need to do at this point, instead of going straight in and multiplying it all out, I want to start by reducing whatever I can here. Now it's a little bit trickier because now I have multiple things that I'm multiplying up here. I have the 200, the 2, and the 4 that I need to multiply. So to reduce this fraction, I'm only going to choose one of these numbers and use that to reduce it along with the bottom part, the denominator. So choose a number in the numerator to reduce along with your denominator. I'm going to choose 200 because I know that 200, since it's the biggest number here, if I can reduce 200 down, then that's going to save me from having to reduce again and again and again and again. So I'm going to look at 200. And let's do a little circle here. And then I'm going to try to reduce that with 360. So if I look at these two numbers, right away I know that I can divide both of them by 10 because they both have a 0 at the end. So that lets me divide the top and the bottom by 10. And so that'll give me, I'm going to rewrite this, 20 in this case. 200 divided by 10 is 20 times 2 pi times 4. Then on the bottom, 360 divided by 10 is 36. But now I still notice that I can still reduce 20 and 36 because both of these have a factor of 4. So if I divide 20 by 4, then that'll give me 5. And if I divide 360 by 4, then that'll give me 9. And yes, you do have to do this as far as you can reduce these fractions. You can use a calculator to help you out to find the greatest common factor between them that you can use to reduce these. So, but I know just from off the top of my head, and because I'm a math teacher, that 20 divided by 4 is 5. Then over here I have 2 pi times 4. Then on the bottom, 360 divided by 4, like we said, that's 9. Yes, because I'm a math teacher, I know these factors. But like I said, if you're not sure, always double check with a calculator. So now, let's see. Yep, there's nothing else that I can reduce here. I can't divide 5 into 9 or 2 into 9 or 4 into 9 anymore any further. So now let's just multiply everything we got. So again, in the interest of keeping this in exact form, I'm going to ignore that pi and multiply everything around the pi. So I have 5 times 2 times 4. I know 5 times 2 is 10. 10 times 4 is 40. So on the top, I get 40. And on the bottom, I get 9. And then I just make sure to bring that pi back in. Since the pi is on the top, I want to keep it at the top. And there is my arc length in exact form. Now go ahead and plug this 40 pi over 9 into the calculator. And you're going to find that's the same as our decimal approximation. So if you do this, you check it, you're good to go. Got one more example here, so let's take a look at that. What is the area of a sector in a circle with a diameter of 22 meters and a central angle that measures 100 degrees? So since I have no picture here, I'm going to draw one. So there's my circle, perfect circle, of course. And it tells me the diameter is 22 meters. So I'm going to draw a line here, and that's not exactly to the center. That looks better. And we're going to say this is 22. And then I have a central angle of 100 degrees. I don't know how much exactly that is, but I'm going to guess something like that. And we know this is 100 degrees. And so we're looking for the area of the sector, and I'm going to highlight it in yellow, the sector of the arc that measures 100 degrees. So we're looking for this sector, the area of this sector. So I know that I'm going to use my formula for area of a sector this time. So my formula for area of a sector is, I'm just going to write it out in red. Area equals theta times, since it's area this time, we have pi r squared divided by 360. So there's our formula for sector area. So we need the arc measurement, which we know is 100, and we need the radius. Now we're not given the radius, we're given the diameter. But remember that the diameter is the radius times 2. So to find the radius, I can divide by my diameter by 2, which gives me 11. So I know that the radius is going to be 11. So let's plug what we have into our formula. So the sector area equals our theta here, it's 100 degrees, times pi radius squared. We know the radius in this case is 11 squared divided by 360. And so I can start reducing right now, but I'm going to multiply out the 11 squared first to see if there's any factors there that can also help me. So A equals 100 times pi times 11 squared is 121 divided by 360. So in this case, it didn't help because 121 has no other factors besides 11 and 1. There's nothing else that I can multiply except 1 times 121 and 11 times 11. So that doesn't help me, but that's okay because I'm going to need to multiply that out anyway. So I have that done. So I'm going to look at 100 then. Is there any way, any factors in common between 100 and 360? Yes. And I can see right away that because both of these numbers have 0 at the end, then I know that 10 must be a common factor between them. So I know that I can divide the top and the bottom by 10. So when I divide the numerator by 10, I'm going to write A equals 100 divided by 10 is 10. And I'm going to write out pi and 121. And then on the bottom, 360 divided by 10 is 36. Now I can still see factors between them. And if you're not sure, remember, you can always put it in the calculator, plug in something, 10 divided by something, see if it works out, then divide 36 by that same something to see if that works out. For example, if I have 10 divided by 2, I know that's 5. So if I try 36 divided by 2, that gives me 18. So I know that there's still some more factors here that I can take out. So from the 10, I can divide that by 2, and the 36, I can divide that by 2. And so I get A equals 10 divided by 2 is 5 times pi times 121 over 36 divided by 2 was 18. And so now I'm checking to see if there's anything else that I can factor out or anything else that looks factorable. And I don't see anything, so we're good to go. So the next thing I'm going to do is multiply what I have in the numerator. And again, I'm going to ignore this pi and multiply everything around that pi. So I have 5 times 121, which gives me 605. And no, I didn't know that. I did this beforehand, so I don't have to switch over to the calculator and waste time and make this video longer than it should be. And then I have that over 18. So I have 605 from 5 times 121. I bring the pi back in, and then I have over 18. So that is my exact form. Now remember, if you're just looking for the approximation, you can just plug it in from the formula in here. Plug this into the calculator, and that'll give you your approximation of 105.59. But when you get your exact form, if you plug that in, you should end up with the same number as your decimal approximation. And that's it, guys. In our Google Classroom, I have posted these notes. This is a little cheat sheet with the formulas for arc length and for sector area. And I love these faces. They're so cute. So use this while you're working on assignment 8.7 to help you out. If you have your formulas in front of you, it's a lot easier to work out. Remember, I'm hoping that you try to work these out in exact form, but if you can't, always use the approximation to double check your work. Okay? So that's it, guys. That's it for today. So I'll see you guys next time. Study hard. Remember to reach out if you have questions. And I hope you guys have a great day. Take care, and I'll see you next time.